Our next speaker, Lochlin Ermatinger from Montana State University, mapping wheat stem sawfly infestations. Lochlin is a graduate student at Montana State University in Bozeman, Montana, studying how remotely sensed data can be used to map infestations of wheat stem sawfly in wheat fields. He started working in David Weaver's wheat stem sawfly lab as an undergraduate, dissecting thousands of stem samples. A graduate program has offered him the chance to incorporate his knowledge of geospatial technologies and remote sensing with on-the-ground surveys to investigate possible avenues of mapping wheat stem sawfly infestation. Lochlin.
Thank you. Well, I'd like to say thank you to Farming Smarter Canada for inviting me up here to, of course, speak about the work I've been involved with at Montana State in David Weaver's wheat stem sawfly lab. And it sounds like some of us in the room are familiar with Sawfly, and especially in a research capacity, this is where I began learning about the pest as an undergraduate. And if you're an undergraduate working with Sawfly, that means you are dissecting an endless amount of stems. Because as we just learned about in the last talk, the Sawflies spend 95% of their life cycle within the stems. So if you want to understand what's going on with sawflies, that's where this work begins and ends. And at the time, I was studying remote sensing and GIS, and I realized, well, maybe we can bolster the efficiency of these stem dissection surveys and use something like remote sensing to get better ideas of what's going on in the field. And so today we'll talk about how we use remote sensing in agriculture as a method. We'll talk about what some of the specifications for wheat stem sawfly might be. And then we'll end talking about where I see some of the future work for this lies. So what is remote sensing? Well, it's essentially the process of detecting and monitoring physical characteristics of an area by measuring its reflected and emitted radiation from a distance. So we usually think about using drones, satellites, or planes for this. But I think a more appropriate definition for remote sensing for agricultural science is combining pictures of light, both seen and unseen, with data collected from locations on the ground, and creating a statistically defensible model that we can use to then estimate that property across the larger area, aka the rest of our field. And the reason I say that is because we need three things to do this. The first thing we need is our ground observations. And so this could be something like soil pH, our yield, or in today's case, sawfly infestations. And then, of course, we need those remotely sensed images. And once we have that, we can use statistics to explain the variation in that property across the ground with the variation that we're seeing in our images. And then we can produce a map that we have some level of confidence in what that map is saying. And so remote sensing data comes in two forms. First form of data we refer to as active. This is when a sensor uses its own radiation to measure its intensity of return. And this is often done with sensors like LiDAR or radar, and it's ideal for understanding the structural nature of vegetation. The other form, which is more common, comes from passive sensors. This is when a sensor is just measuring that reflected, naturally occurring radiation, and this comes in two forms, either multi or hyperspectral. And those words just refer to the spectral resolution, or how many measurements is that sensor recording across the spectrum of light. And for my degree, I was using these two types of data. And so the first form, being hyperspectral, is essentially the hyperspectral fingerprints of plants. And this is really good for understanding the chemical or molecular composition and variation within plants. So as we know, plants are green because pigments absorb blue and red light and reflect a bit more green light. And then if we move on to the near infrared, that region we largely think of as being controlled by the mesophyll tissue. So the integrity of that tissue will actually reflect radiation there. And then out in the shortwave infrared, that's largely controlled by the water content. So we see there's a lot of absorption there. And variation within this fingerprint is related to a number of things. The phenology of plants. Over the course of a plant's life, it's going to look different depending on what stage it's at. Different varieties are going to have subtle differences in their structural composition that's going to change how they interact with light. water status. So if this plant was water stressed, we might see elevated reflectance out in the shortwave infrared. Things like our fertilizer rates. So if our plants aren't getting enough nutrients, of course, that's going to impact how they can utilize radiation. And then, of course, things like diseases and pests can have their own impacts on how plants use light. And so hyperspectral is concerned with the same spectrum of light, but instead of collecting hundreds or thousands of measurements across that spectrum, we're now collecting anywhere from 3 to a dozen or more. And so on this graph, we see the distribution of what are called bands of some of the popular remote sensing satellite. And a band is where a sensor has a filter to aggregate all the light within a group of adjacent wavelengths and record a single reading. And so these are some of the popular agricultural satellites today. We have MODIS, Landsat, and Sentinel-2, and then Planet Labs down at the bottom. And we notice they all have pretty similar spectral distributions of where they're looking at light, but they have differing spatial resolutions, so what pixel size comes in at. And so now this idea of spatial and spectral resolution brings up the idea of dimensionality. And so anytime we're beginning a remote sensing project, it's important that we understand what our data should look like on our spectral, temporal, and spatial dimensions to capture the change we're interested in. So of course, first we have our spectral dimension. So if we were setting out to look at something to do with water, whether that's prevalence of irrigated fields or drought, a satellite like Planet Labs might not be the most sensitive or best fit because it has no bands in the shortwave infrared. And then of course we have our spatial and operational scale. So this means, if we were setting out to map shapes or something like that, of course if we had coarser pixels, we would be doing not so good of a job of identifying what we're interested in. And with Sawfly, we can think about, okay, well, what does Sawfly look like, infestation look like across the field? Well, we know it's largely an edge effect pest. So in this field, we're seeing the greatest rates of infestation at that edge, closest to what was heavily infested wheat the year prior. And then we can see it dissipates as we come inwards. So this can lead us to ask questions like how far apart should our measurements be to adequately capture the change in infestation throughout our field? And then, of course, how many measurements do we actually need? And now, this brings up the idea of, okay, well, when do these measurements be collected? And this is thinking about our temporal dimension. And this is something we don't hear about, or at least I don't think we hear about enough. And so that's when do we need to be collecting these data? And so for the Sawfly, we need to understand how it interacts with its host. So we know that the Sawfly emerges at some point in the spring. And during this time, the adults are looking for a host to lay their eggs in. Females will probe just about any grass, wheat, or barley stem they run into. But we know that the females have a preference for the hardiest stems that are available. So beyond the edge effect, there might be some value in monitoring fields in these early season conditions before or concurrent with Sawfly emergence, because there could be some variability that's slightly influencing where those Sawflies spend their time and in turn where they lay their eggs. So after that, these eggs then hatch and they feed up and down the stem, feeding mostly on the pith. And the Sawfly is beholden on the stem it was laid in. So that's kind of its home, right? And so it doesn't make sense that it's going to really do a ton of physiological damage that's really going to show up within a satellite image. There could be some subtle cues, but if you've been out in your field in July and you're just looking at stems, it's very difficult to say this one's infested, that one's not. But there still could be some value at studying this point in time. Then at the end of the season, when the crop ripens, the Sawfly descends to the base of the stem, at which point it earns its name by sawing the stem in a circular motion. And so when this happens, it'll actually cut that stem. And this is when Sawfly infestation is, of course, most detectable. And in fields or areas of fields that have heaviest amount of cutting, those cut stems can fall over and they can bring a lot of stems with them and create these areas of lodging. And so this seems like a good starting point for remote sensing of Sawfly, but I don't think we should solely rely on lodging for remote sensing of Sawfly because, of course, it can be caused by things other than Sawfly. And then, of course, even in fields that have heavy cutting, the rates of cutting can depend on a lot of factors. From a remote sensing standpoint, we might not want to bank on collecting images concurrent with the maximum extent of lodging. And then if we're just focusing on lodging alone, we might be underestimating what the severity of sawfly infestation is. And of course, as we just heard about, we could be missing important events like parasitism. And so I think there's value in starting with studying all of these standpoints, or these time points, because they all are telling us a different piece of the story of sawfly and its host. And so now this brings us to, okay, well, when do we actually go out there and collect these measurements of infestation? And so in studying sawfly, I think some of the most valuable measurements come from the end of the growing season, because from the time an egg or multiple eggs are laid within a single stem, there's a lot of factors that can happen throughout that growing season that are going to determine if that stem is cut or not. And then beyond that, there's not too many in-season management techniques available. So if we can get a good idea of how many sawflies are going into that next winter, we might have a better idea of what to do or what to expect for next year's pressure. And so the technique we've been using is to go out to a field post-harvest and collect a number of stem samples from across that field. So for example, this was just a 32 hectare field, and you can see our sampling blocks across it. So we grabbed 100 samples, and the reason they're placed in these blocks is because to do this configuration, that was about 7 miles walking. So if we're doing a regular grid, I don't want to know what that number is. And for each of these samples, what we do is we grab all the stems within 30 centimeters of a row. We then take those back to the lab, of course, and we dissect them individually to quantify, what the extent of feeding is and note things like parasitism. And so this brings me to the hypothesis of my graduate work, which has been that estimating the level of wheat stem sawfly infestation at wheat at the end of the growing season will benefit from integrating spectral measurements recorded across the entire growing season. And so before trying this in the field, I had to do this in the greenhouse. And so I did a greenhouse project where we were evaluating the potential of using hyperspectral measurements for estimating the percentage of sawfly infestation. So essentially emulating the data that would be captured by a hyperspectral drone. So I used a sensor that collected over 2,000 wavelengths across that region, oriented that sensor above the plants I was growing so that we were emulating a pixel at about 30 centimeters resolution, just similar to how drones operate. And then I started collecting measurements from before introducing sawflies all the way up until those plants were senesced and ready to harvest. And so for my ground observations, I was thinking about infestation as a percentage, or within each pot, how many stems were infested by sawfly. And the reason for that is when we think about what these pixels look like or what they're capturing, it's an aggregation of everything within that pixel. So I think it makes the most sense to think about it as the percentage of infested stems within a pixel. So to do that, we grew wheat in the greenhouse, and we used the spring wheat variety reader, grew that in large pots. And green wheat, or reader, is a spring wheat variety that is susceptible to sawfly. And the reason we use that is because it's very difficult to get sawflies to actually infest in the greenhouse. And so if you can use a hollow stem variety that is actually getting infested, you have a good model for what the sawfly can do to its host. So we put 10 seeds in a pot, and this turned out to be about 25 tillers per pot. I used 100 pots total, and 78 of those were viable throughout the entire experiment. And of those, I withheld 19 for controls. The other 59 got sawflies. And to do that, we're rearing these sawflies alongside these plants. And once they emerge, then we take 20 newly emerged females. We put them in enclosure nets around our plants. We give them 3 days to infest, and then we remove the nets. And so to collect the hyperspectral measurements, I had to come up with my own contraption that would orient our sensor up at the top, and then use some contractor lights because they have halogen bulbs that are surprisingly full spectrum emission. So that's compatible with our sensor. And we made it so that the top of that could move up and down. So as these plants grew up and grew out, we could maintain that 30 centimeter pixel size. And so for this experiment, for each plant, you get 9 readings. And when you stack those 9 readings together, you get this 3-dimensional shape where we have wavelength on one axis, days after infestation on the other axis, and then our reflectance going up. And so now the challenge becomes, how can we sort through these 12,000 data points and use this to estimate the ending infestation level? But first, I need to tell you guys how we dissect those stems to actually categorize infestation. First category is, of course, uninfested, where a stem has no sawfly and no frass, which is their excrement. Then, of course, there's sawfly cut, when we have multiple nodes burrowed through and that stem is eventually cut. And then there are some cases where they burrowed through nodes but died before cutting the stem. And then something called a dead neonate, where a larvae fed for a couple days, never made it through a node, and we think its feeding was pretty negligible. So we were most interested in the most damaging forms of infestation, and in this paper we called it adequate infestations, which was the proportion of stems that had multiple nodes burrowed through or were cut, divided by that total number of stems. And so when we look at how this played out across all the samples in our experiment, we get, observations across this gradient, where we have some with 0 infestation, some with lower levels, and then you'll notice we didn't get too many above 50% infestation, and that's just due to the difficulty presented in actually getting all your tillers infested in the greenhouse. And I think I forgot to mention earlier, but we introduced them at Zadox 32, and that's when that first joint is detectable, and so that's the first stage when a sawfly can infest a stem. So now that we have our data, now we need to use a model that can look at that 3-dimensional reflectance, can estimate what that ending level of infestation is. So to do that, I used a multivariate statistics model called sparse multi-way partial least squares regression. And so all that means is it's a multivariate model that is designed for looking at high-dimensional data sets like this. And that word sparsity means it can look through the combinations of time points and wavelengths, discard what's not important, and find relationships that are very difficult for us to come up with. And so to actually do this, I take my full data set, give my model 85% of the data set to train, and then I withhold 15% of it to understand how well this model is at estimating that property of infestation. And so again, we're just sorting through all those combinations of wavelengths, time points, and it uses something called latent variables to actually do the regression. And so the output of this model, here we have the predicted value on our x-axis and the observed value on our y-axis. So if this model was 100% accurate, our points would be all on that line. That doesn't happen in biological data, but we can see that our points track pretty well with it. And this actually explained about 68% of the variation in our sawfly infestation. And so on average, this model is also about 13.5 percentage points away from predicting that actual value of infestation, which is pretty good for just using that spectral data. And so now when we're thinking back to, okay, well, what light is important and when is it important? This graph shows us the wavelength on the x-axis and the days after infestation on the y. And this is the distribution of data that was chosen by the model. So if it used all the data it had access to, there'd be no white space, but there's a lot of white space. This model used about 3% of the data it had access to. And we noticed that there's a cluster in that green light that is chosen for all time points in the experiment. We noticed the same pattern going on in the near infrared. And then interestingly, in that shortwave infrared, this is where most of our wavelengths were chosen, and we have this kind of diffuse pattern. And so again, when we're thinking back to that temporal dimension, okay, well, when is light important? We see that none of these time points were discarded, and they all had some value. And so, we were able to explain only about 68% of that variation, and there was no one time point that was chosen or none that were discarded. So I think it shows that, sawfly's effects on its host are very subtle. And so we benefit from observing that entire growing season and integrating that data. And so when it comes to the field, when we're thinking about, okay, should we use a drone or a satellite? Well, we know that, or at least we like to think that the more measurements over time, the better. That makes it difficult to fly a drone once weekly. Another thing that makes it difficult is not too many drones collect data in the shortwave infrared or in a hyperspectral sense, but we see that a lot of our satellites collect light throughout that spectrum that showed up as important. So I think they're all beneficial, and with the scale that we grow wheat at, I think a satellite is probably a better tool. And so with the rest of my time, I'd like to briefly present using this approach in the field. And so back to that field I was talking about earlier, this was 32 hectares seeded to a hollow stem variety of winter wheat called Brawl. Again, we grabbed 100 samples, and when we were grabbing those samples, one thing I thought about is where was last year's wheat? Because I wanted to make sure that I was capturing the vectors of the areas where sawflies might be entering that field. And then, of course, I grabbed one big block of samples from the interior. And I chose Sentinel-2 because it has good coverage across that spectral gradient. It collects 13 bands, and it records an image every 5 days, depending on your location. So I grabbed all the cloud-free images from beginning of May until harvest, and that came out to be 16 images for this field. And again, I use that same approach with that sparse multi-way partial least squares regression, where I give it most of my data to train, withhold the rest of it to validate, and then I can interpolate that across the rest of the field, and we get a map that I think looks pretty close to what we'd expect Sawfly infestation to look like, where we have some of the highest infestation predicted along our edges, and then as we move inward, it tends to dissipate. This model actually performed slightly better than our greenhouse example. Now we're explaining about 85% of the variation in our validation data set. And on average, this model is about 9.6 percentage points away from the actual value of infestation. So in summary, this is just a start with this type of work, but I think one of the key takeaways for me is that, integrating all the images over the season, that's going to help our model performance. And then, of course, well, what's the application of having a map about sawfly infestation at the end of the season? Well, there's a lot of tactics out there for sawfly right now, but there's not really a concrete strategy. And I think a lot of that lies in the difficulty in getting good estimates. And so I think if we can go into that next year with a clearer picture of what we might need to expect year after year, we can start to understand what's going to work and what's not. And so, maybe planting something like a solid stem variety makes sense based on the pressure we'd expect for that next year. And then I think as an overall supplement to all the research projects that are going on, as we just heard about, there's a lot of benefit for the parasitoids, but it's very difficult to actually quantify the benefit they provide. So if we can put some numbers behind the interventions we're using, I think that can help with our management and maybe one day lead to control. And so in thinking about the future work, I think this shows pretty good promise for using passive or optical data across that entire growing season. But as you might have noticed, I didn't use any LiDAR active type data. And I think there could be benefit in integrating that right at the point of cutting. So maybe using something like a LiDAR drone or synthetic aperture radar and creating some type of fusion model. And then, of course, this was just how I decided to do sampling for a 2-year degree. And so there's a lot of work that needs to be done to understand, okay, spatially, what's the optimal way to do this? Because as we know, sawfly is just one of many things going on in the field. And as we've heard about in a number of these talks, everything works better when we understand all that's happening in our field and understand not only, in my case, how sawfly varies, but how things like soil conditions or herbivory from other insects varies with sawfly infestation. And so just to reiterate that, when we're thinking about our drone or satellite imagery, it's a composition of everything that's going on underneath it. And in today's day and age, it's kind of the golden age of remote sensing. There's thousands of images being collected every day. There's cheap computing power, there's AI, but we're not getting any more data from the ground. And there is no substitute for having surveys done from the ground, unfortunately. But I think the more of it we can collect, the clearer picture we can get, and the better we can tell what works and what doesn't. So with that, I'd like to take some questions if I have time. And if you'd like to read more about the methods from that greenhouse paper, there's the title for it. And of course, feel free to reach out for an email. So thank you.
I do have a Slido question. What's one thing you've liked the most about your master's experience?
That's a good question. Yeah, I mean, I didn't know what to expect going into it. A lot of interdisciplinary work. Learning about Sawfly was a big thing. Lived in Montana my whole life, but not spent a whole lot of time on farms. So, understanding all that goes on in those fields, I think is very eye-opening from somebody from the outside. So I think that was kind of one of my biggest takeaways.
Any questions from the floor? All right, I guess not. Thank you very much, Lochlin.
Thank you.